All right, well, welcome. In this video, we're going to be looking at lesson 5.6, which is going to be about finding the inverses of functions. But let's review what an inverse is. An inverse relation is any, and this is in that gray box there at the top of your page. It says an inverse relation is any set of ordered pairs, x and y, where the roles of the independent variable, which is x, and the dependent variable y are reversed or flipped. So let's look at this example here where we have a table of values. So in this first table, where we have the column for x and y there being the values for x are -2, -1, 0, and 1. The values for y are 1, 4, 3, 1. What we see that every single x is paired up with a different y. And that makes a function. Okay, so the definition of a function is where each x is paired up with a different value for y. It's kind of like a function or like a snack machine where if you type in a code like B5, you'd expect that if you type in B5, you would just get a Snickers candy bar, whatever you see when you look in the window. But if you type in B5 and then you get a Snickers and you type in B5 again and out comes a bag of M&Ms, well, that's not a good working snack machine because you want to expect every time you put B5 into that machine, you'd expect to always get a Snickers or whatever the case would be. So in this situation, we could see that when you put -2 in, you get 1, -1 in, you get 4, put 0 in, you get 3, and put 1 in, you get 1. So that is a function because for each individual x, you have one output, one answer for y. Now the inverse basically just takes the x values and y values and switches those. So you see what happened there. So what was the y values is now our x values, and what was our, oops, that doesn't show up very well, but what was our, this will show up better. What was our x values is now our y values. So you can see that the x and y values switched. And so now let's look to see if that's a function. Now, one way that you could do that is you could reorganize. So that third table there, what they did is they reorganized those values. And the important thing is to recognize that when you put 1 in for x, you get 1 for y. But when you put 1 in for x, you also get -2 for y for this function. So that would be like that example where if you put B5 in and expect to get Snickers, and you put B5 again in, you get a bag of M&Ms, that's not a good snack machine. So that's what this is here. This is not a function. Okay, you don't have to always reorganize the values. You can just look here at this table and see the same thing. But the key there is to recognize that it's not a function when you're looking at a table if you have a value for x that's paired up with two different values for y. So let's look at this example here where they give us, so tables can be done horizontally, they can be done vertically, so don't get confused by that. So this one, the table is horizontal, and we want to figure out if the inverse is going to be a relation, or if the inverse is a function. So the first step is to figure out what is the inverse. So I'm going to switch these around. So the values that were the y values are now going to be my x values. So I'm going to put these down, 9, 7, 5, 3, 1, and -1. And now the values that were our x's are now going to be our y's. And so this would be -1, 0, 1, 2, 3, and 4. So when I look at these, I want to look to see if there's any repeats in the x's. So I have -1, 1, 3, 5, 7, 9. There's no repeats with the x's. Okay, so then that tells me that every x is paired up with its own unique y. If you're wondering what the heck I just did, let's look back at the previous example. When I look at these x's, I see that there's repeats, and so then I want to check those out a little further, and I see that when this x is when the first x is 1, the y value is -2. When the second x is 1, the y value is 1. So that's how you can check to see. Now, if they had both been -2's, then that would count as a function because they're both paired up with the same value. All right. To be honest, we're not going to work with tables. It's always good to look at that as a start, but we're not always going to be working with tables. Oftentimes, we're going to be looking at equations. So to find the inverse of an equation, we're going to switch the roles of x and y, meaning that anytime you see an x, you're going to change it to a y. Anytime you see a y, change it to be an x, and then you solve for y, which, depending on the problem, might involve a little bit of work. So let's find the inverse of y equals x squared. So just like we're going to follow that first step, step 1, we're going to switch the roles of x and y. So instead of y equals x squared, it's going to be x equals y squared. We're going to go to the next step. So the next step is to simply solve for y. So we want to get the y by itself. So to get the y by itself, we would take the square root of both sides. Now remember, when you take the square root of both sides, that means that there's going to be two solutions, a plus or minus. So your answer would be plus or minus square root of, whoops, oh, I put square in there. So it'd be plus or minus square root of x would be your answer. Okay. So then this is the graph of y equals x squared and its inverse. So the square root of x, remember, would be like this, but then we would have negative square root of x as well. So that's how we get this parabola that's been tipped over sideways. So that's how we get that shape. So that tipped over parabola, that would be the inverse of the graph y equals x squared. Now let's look at what that says though. It says graph y equals x squared and its inverse. Is the inverse a function? How would you describe its transformation? So let's review how to tell if something's a function or not. If we can draw a vertical line, and no matter where we draw a vertical line, it passes through only one point of the graph, then it is a function. So y equals x squared, that's a function, because it passes the vertical line test. But this one clearly does not pass the vertical line test. So the inverse is not a function. So the way that you can tell is if you graph the inverse and it fails the vertical line test, it's not a function. Now, we also have what's called a horizontal line test. Now, sometimes you don't want to take the time to graph the inverse, but let's say if I was just looking at y equals x squared and without having to graph the inverse, I wanted to see would the inverse also be a function. Then we have what's called the horizontal line test. The horizontal line test is that if you can draw a horizontal line, and if it passes with only just, so if it passes, that means that it's only going to cross the graph at one point. So this one, it fails the horizontal line test. So that tells me that the inverse would not be a function. Where if instead, if I had a graph like this, so that's like the cubic function, and I wanted to see, would the inverse of that be a function? I would draw a horizontal line and be like, yeah, no matter where I draw a horizontal line, it passes. It's only going to pass through one point. So since this passes the horizontal line test, the inverse would also be a function. So that's all you can tell if a graph's inverse would be a function is by using the horizontal line test. All right, let's look at one that's a little bit more trickier. Let's look at this one together. So we have f of x equals 2x plus 1. So remember, to find the inverse, the first step is to find out we have to switch the x and y values. You might be saying, well, wait a minute, there's no y value here. Remember, f of x is the same as y. So the first step, when we change the x to a y and the y to an x, this will be x equals 2y plus 1. And now the second step is to solve for y. So to solve for y, I'm going to start by subtracting 1 from both sides. So this will be x minus 1 equals 2y. And then I would divide both sides by 2. Now, technically, I could leave it like that, but I want to write this better. So this would be the same as dividing both the x and the negative 1 by 2. So yes, you could write it as x over 2, but I'm going to write it as 1/2 x. It's the same thing, minus 1/2. Because now I can easily see that this is a function. Because that's a line in slope-intercept form. Our slope is 1/2. Our y-intercept is negative 1/2. So have a y-intercept at negative 1/2, and then we go up 1 over 2 units. So the graph would look like that. So that passes the vertical line test. So 1/2 x minus 1. It is a function. It's a linear function. So you don't have to worry. You wouldn't have to graph it. If it's a linear function, you just know that that graph is a function. And then the part B, it says, how can you use the graph of f, the original function, to determine if the inverse is also a function? Well, if we graph the original function, y equals 2x plus 1, so this would have a y-intercept of 1. Okay, so the y-intercept is our b value. Our slope is 2, so we go up 2 over 1. So that's the graph of y equals 2x plus 1. Again, that passes the horizontal line test, so that's a way to tell that the by looking at the function of, or the graph of f, to tell that its inverse is a function is by using the horizontal line test.